The paper about out of distributions? No? Lingjun. No, it's not. Okay, the other presenters. Oh, Lei, you are in the room, right? Lei? Shen Lei, do you want to try? So we will start at 11 in 6 minutes. Do we have the presenter of the second paper?
Pardon?
The
Begin now?
second paper. No.
The second.
I'm asking who is presenting the second paper. An empirical study of robustness of DNN with out of distribution. Is the speaker in the room?
Hello. Yes.
Okay.
I'm the author of
Okay.
second paper.
Okay. Good. Okay. I think we can start while other people are joining. So welcome everyone in this session. And thank you very much for joining us in this interesting session on software engineering and AI. I'm looking forward to the talk. I hope you will enjoy the talks. So in this session, we have three interesting talks. The first talk, it's about floating point accuracy verification in deep neural network. And it will be presented by Chaojin Wang.
Yes.
So without further debate, please start. The talk are around, I think, 20 minutes roughly, and then we can have some discussion. So we have only 3 papers in the session, so maybe we can have more discussion. So if you have question after the talk, don't hesitate to ask the question. You can either ask through the chat here. I think it's more convenient if you ask it here in the chat. Or you can raise your hand and then I can allow you to ask the question. So please proceed.
Okay. Thank you very much for giving this opportunity. Give me opportunity.
Can you make full screen the PowerPoint? Can you go in presentation mode, please?
Pardon? The sound is very small. Yeah. Okay.
You are not in presentation mode. Yeah.
Okay. Okay. I can begin now.
Yes. You can begin. Yes.
Okay. Thank you. Oh, hello everyone. I'm very pleased to have this opportunity to present my paper here. Here is my paper title: Floating Point Accuracy Testing in Deep Neural Network Computations via Hypothesis Testing. Yeah, the outline contains five main components listed as below. Yeah. First is motivation. Look back at the history of mobile AI, and you find that deeper learning neural networks is used very popular. And the running depends highly on the server and depends highly on the ASIC circuit named as a MPU or DSP or other processing unit name. And since the resources are very limited in smartphone, and in the smartphone, it only it commonly used is float point 16. But traditionally in server and personal computer, we use float point 32. So data type conversion are often data type conversion or other operations from original float 32 to float 16 are often involved. Here, we call the software and hardware platform accelerator, like Huawei High AI or Qualcomm SMP. One of the challenges is how to assess the accuracy performance of different accelerators. First, let me introduce some relative knowledge. The large majority of DNN floating point computation plays a leading role. For AlexNet, multiply edge is of more than 99%. However, floating point accuracy loss exists widely during computation. The most commonly used approach to test floating point accuracy is by comparing with a benchmark platform such as TensorFlow. Here is the formula. An inequality used to check if test data holds. Data ACC and data BM are the results of the accelerator and the benchmark platform with the same inputs respectively. If this formula is satisfied, it is determined that the accuracy is consistent with the design specification. Obviously, drawbacks exist. There are two typical drawbacks here. First, silver parameter A2L and R2L must be vary while the absolute of data ACC and data BM increase. Second is no quantitative measurement for this method for the accuracy loss. The IEEE has a standard to represent the floating point number. Here is a representation. It is composed of three components: the sign bit S, the component E, and the mantissa M. And the mantissa M. A real value assumed by a given 16-bit floating point with a sign S and the component E and mantissa B can be expressed as this formula. As this formula, by this presentation, we can know it has five accuracy loss cases. First is overflow or underflow. This means that a computation caused the absolute of a number bigger than floating point maximum, or the absolute of a number is less than the absolute minimum. Second is rounding. Because of the rounding, floating point forms is not associative and is not distributive. Third is the conversion between different floating point forms, like floating point 32 and floating point 16. Fourth is the different algorithm. In my paper, I give an example. Like we calculate the reciprocal of X. There are two algorithms, Newton's method and Taylor's theorem. Finally, is the implementation is not perfect. We must optimize the implementation continuously. Interestingly, the loss of a floating point accuracy can be treated as a problem of probability. Specifically, hypothesis testing is introduced in this paper. Under a given assumption, a certain quantity would be calculated, and it allows us to interpret whether the assumption is held or violated. The assumption of a hypothesis testing is often named as a null hypothesis, hypothesis 0. The opposite of the null hypothesis is named as the alternative hypothesis or hypothesis 1. Correspondingly, or hypothesis 1. In hypothesis testing, we accept or reject H0 according to a certain degree, the significance level denoted as alpha. The smaller alpha is, the more robust the null hypothesis. The more robust the hypothesis is. There are two approaches to determine the result of the hypothesis testing: rejection region approach and the p-value approach. In this paper, we use a p-value approach. Back to our problem: how to determine a 16-bit floating point accuracy to be accepted or rejected. Here we here is the accelerator. It involves the 3 parts: input and output and the specified computation. The specified computation can be a commonly used operator, like a convolution or softmax or other operator. Since 32-bit floating point has a far larger range and higher accuracy of expression ability than 16-bit floating point. That is, the former is at least 4 orders of magnitude smaller than the latter in terms of in terms of the minimal data interval, So we take a 32-bit TensorFlow computation as the benchmark. Here, given OT as a target accelerator, as our target accelerator, that is the system under test. OTF32 as a TensorFlow output, we observe below variable from the perspective of statistics. Here we're taking convolution as an example. Its mathematical prototype is like this. We will verify if the output CMN, which is as the OT of the testing 16-bit floating point accelerator. For our this accelerator used in our experimentation is high. Is consistent with its 32-bit TensorFlow in perspective statistics. The proposed framework is shown here. First, generate testing data. It can be obtained from a DN operator computation, both in a target accelerator and benchmark accelerator, like TensorFlow. Next, we select a hypothesis testing strategy. Specifically, in our paper, there are 2 strategies: Z-test and T-test. At the same time, H0 and H1 will be created according to our target. Based on selected target, we would calculate a specific probability P probability P of rejecting the null hypothesis H0. The smaller P is, the more probable P is rejected. P is rejected. Finally, we make a conclusion of the floating point accuracy on target accelerator. If P is smaller than alpha, the significance level, the conclusion is reject H0, which means the accuracy is not in the range of acceptance, and the information should be provided to provided as developer feedback to discover how to optimize the implementation. Of course, the implementation includes software implementation and hardware implementation. Actually, in practice, we mainly optimize the software implementation. Now, take a look at z-test method. Here is a here is a representation of z-test. The horizontal axis and the vertical axis are calculated the calculated statistic and the probability density. It has two properties of one-tilde and two-tilde. The two-tilde is more applicable for our problem. We use z-test to determine if the means of a set of observation samples are significantly different from the population under two prerequisites. First is the from the population under two prerequisites. First, the first prerequisite is the population under the null hypothesis can approximately follow normal distribution. Second is the population variance have been already known. For our problem, the observation samples are the difference between the calculation output of the target accelerator and our benchmark accelerator. This is OTF TensorFlow, OTF 32. The difference, this variance we focused. The mean of the population mu 0 will equal to 0 theory. So the null hypothesis and alternative hypothesis can be described as this. Statistic Z can be calculated by this formula, where N01 is the standard normal distribution. The second method is the t-test method, shown in this figure. As the degrees of its freedom increases, it approaches to the normal distribution. It has one prerequisite: the population under H0 can approximately follow normal distribution. Compared with z-test, the population invariance sigma squared does not need to be known. Similar to z-test, we can list the hypothesis and the statistic t and other formula like this. To evaluate the performance of our proposed methods, we select higher and TensorFlow as our accelerator. Here are their versions respectively. The typical specified DNN operator selected with TensorFlow is TensorFlow is tf.n.conv2d. We first randomly generate a normal distributed sample with a mean value 0. Then we can calculate and obtain OT. Here the target accelerator is higher, and OTF32 and OTF16 and OTF16. After confirming the approximate normality of OTA minus OTF32, we can calculate statistic Z and PZ. At the same time, currently used method scheme denoted as scheme apps is also conducted. These histograms of OT minus OTF32, that is the O high AI minus OTF 32, are drawn here. Include sigma I equal to 1, 5, 10, and 20 respectively. It can be seen that in all conditions, the distributions all looks very fairly symmetric and unimodal. Apart from the figures shown here, central limit theorem under practical large data samples can also prove the normality. In table 1, we illustrate all the calculated statistics and the result of a compared scheme apps. Where satisfy and dissatisfy means the numbers of elements and the numbers of elements that satisfy and dissatisfied are formation in equality. This equality. It can be seen that as sigma I increases, the mean value x bar also increase.
Maybe 5 minutes. We're already 20 minutes. Maybe go a bit faster.
Okay. So the character, this is a character of the natural trend for floating point. In other words, we can't make a decision based on the scheme apps. However, by comparing with the PZ, we can learn that PZ is the mean value, is the here when sigma I equal to 10, it is the worst with the minimum value. In this value, we can, to some extent, it can reflect the floating point computation accuracy level. For t-test, the situation is the same, but it is more simple. It does not need. The difference is we don't need to calculate the population sigma. So no need for OTF 16. Okay, let's make the conclusion. First is a novel idea via hypothesis testing to evaluate the floating point accuracy is proposed. Second is compared to commonly used method. This method focuses on single value used for the compared to commonly used method that focus on single value in industry. Here, the Z-test and the T-test, which is more representative. Third is compared to Z-test, T-test is more suitable for quick using due to its simplicity. Okay, thank you.
Thank you. Thank you very much. So we have time for 1 or 2 questions. So if you have a question, either raise your hand or just write in the chat. I think that would be straightforward. So while people are thinking, I have one question for you maybe. So I'm wondering, you didn't consider like effect size when you compare the distributions? It's not a dimension that you thought could be interesting to see how much of the two distributions are apart? Or is it something you're considering? Like beyond just testing that they are statistically significantly different, maybe also look at the magnitude of the difference using effect size metrics.
Sorry.
So I'm wondering if
can you tell the problem shortly? Can you tell me the problem shortly?
Okay. So you're comparing distribution, right? You're using Z-test and T-test, right? And you're looking using statistically significance, right? I was wondering if I was wondering if effect size, if you could also compute effect size to compute the magnitude of the difference between the two, and if you think it will be interesting in this.
Do you mean how to select the significance level?
Yeah. So the effect size will give you different levels, right, of magnitude between the two distributions. Like if you use a Cohen, for example, or let's say even Cliff effect size, you get different values. Do you think, because it will tell you if the two distribution are quite close or too much apart? I don't know if you think it makes sense in your problem.
Uh, uh,
No?
so sorry, I don't get your point. Yeah.
Okay.
Uh,
We can chat. Maybe I can write down my point.
yeah. Yes. You can write down. Yeah.
I
Yeah.
think
I do not use English delete. So.
okay.
So.
Okay. Yeah, I will write on this so we can. So
Okay.
thank you very much. If there any other question in the audience?
Yeah, I can answer your question in the uh, uh, in the AppSec 2020 channel. Okay.
Yeah, I will write you in the channel. Okay.
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 Thank you.
So thank you very much. Thank you very much for your time.
Okay.
So now we have a second talk, which will be presented by Lingjun Zhou, I think. And it's about the robustness of DNN with out of distribution awareness. So please, can you share your screen?
Now I cannot share because the
The other should
I,
stop. Right? Yes.
yeah, okay.
Okay, good. So this is a joint work from Tianjin University, Nanyang Technology University, and Kyushu. So please go ahead.
Yeah. Hello everyone. I'm Lingjun Zhou from Tianjin University. It's my great honor to introduce our recent work, an empirical study on robustness of DNNs with out-of-distribution awareness. It is a joint work with my partners from Nanyang Technological University and Kyushu University. Currently, deep neural networks have achieved great success in various kinds of computer vision tasks, such as image classification, object detection, and segmentation. As we can see, I can. As we can see in the figure 2, ImageNet challenges that deep learning has surpassed human levels of accuracy since 2015. The common paradigm to train a DL model includes 4 steps. At first, we need to collect enough valid images, and then we randomly slip all images into a training dataset and a test dataset. Next, by utilizing the DNN structure and the backpropagation algorithms, we start to train the DL model with a training dataset and evaluate its performance with the test dataset. Once the model converges accuracy on test data, it is claimed as a well-trained DL model for the given task. And in this scenario, training data and test data satisfies the fundamental assumption of deep learning. They are from independent and identical distribution. However, when we deploy DNN-based systems in the real world, the above assumption is hard to be satisfied. Even though the well-trained DNN models have high accuracy on test dataset, it does not guarantee the correctness in handling data that falls outside of its learned distribution, that is, out of distribution data. Just as shown in the picture, the classifier predicts accurately for cat and dog images, but it shows high uncertainty on OOD image like the million, and fails to give reliable and reasonable results on OOD data. So how to correctly cope with ubiquitously existing OOD data becomes an important question toward trustworthy deep learning. An alternative solution is to empower the DL model without a distribution awareness. Add an extra module to detect OOD examples before the target DL model gives the final prediction. To ease the threats from OOD examples, several OOD detection techniques are proposed. According to the relationship between the OOD module and the DL model, there are two kinds of detection techniques, namely model-based math and data-based math. As shown in the below figure, the green path. The green path refers to model-based math, which relies on features extracted by the target DNN model. And the red path refers to the data-based math, which analyzes statistical features of inputs directly. The OOD module will calculate an OOD score for each. If the score is higher than a predefined threshold, the current input is regarded as an OOD example and will be discarded. Otherwise, the DL model will give a relatively reliable prediction. So far, the data in and out of distribution analysis is still an emerging and active area. There are still many questions need answering. How effective the detection techniques are in a more plausible setting? How is the robustness of detection techniques in an adversarial setting? In the typical training process, we only use in-distribution data to train an OOD unaware model. Then Hendricks introduced a new training paradigm called outlier exposure, which utilizes extra diverse and realistic OOD data sets in the training process to train OOD-aware models. New question naturally arises. What are the differences between and OOD-aware DNN models? So specifically, we address the following 4 research questions in our empirical study. The first 2 questions focus on performance and the robustness of OOD modules, and the last 2 focus on the differences between OOD unaware and OOD aware models. AQ1, the effectiveness of the OOD module. AQ2, the robustness of the OOD module. And AQ3, the performance of DNN models. AQ4, the uncertainty of DNN models. The overview of our study is shown in the figure, summarized as 3 stages. And first, data set and the model preparation. And second, evaluation of OOD modules. And the third, evaluation of DNN models. In the first stage, we prepare datasets and collect OOD unaware and OOD aware models for MNIST and the Cypher-10 tasks to perform subsequent evaluations. In the second stage, we focus on the effectiveness and the robustness of OOD modules and answering AQ1 and AQ2. For model-based and true data-based brand new detection techniques are evaluated in our experience. It's also worth noting that we apply all model-based techniques to both OOD unaware and OOD aware models. In the third stage, we aim to identify the differences between OOD unaware and OOD aware models in model performance, robustness, and uncertainty, and answer AQ3 and AQ4. In our experience, there are in total 2 image classification tasks for different model structures, 8 pre-trained models, and 12 OOD data sets. For each model structure, we trained OOD unaware and OOD aware models respectively. In the experiments, we found 20,000 OOD examples are good enough for outlier exposure to train a good OOD aware model. For each task, we construct a miscellaneous OOD container, which consists of six different OOD data sets. It is closer to the real situation that OOD data are diverse and multi-source. To ensure the correctness of our results, all OOD examples used for training and validation are strictly disjoint with those used for evaluations. So in RQ1, we mix up the same number of in-distribution examples and out-of-distribution examples to identify the best OOD detection technique. As shown in the table, among all detection techniques, the cross-entropy achieves the best detection performance. It has lower OOD scores on in-distribution examples and higher scores on out-of-distribution examples. It achieves nearly perfect detection scores of more than 99% on AURC, AUPR, and TNR95. From the results, we can see that model-based detection techniques generally perform better than data-based techniques in a more realistic setting. Therefore, in the following experience, we will focus on the model-based detection method. We also found that detection techniques with OOD-aware models are significantly better than those with OOD-unaware models. OOD awareness remarkably improves the detection performance and narrows the differences between different techniques. The choice of training paradigms with or without OOD awareness is more important than the choice of different detection techniques. For RQ2, we aim to evaluate the robustness of OOD module and unveil its potential vulnerabilities. Firstly, we randomly replace a small proportion of pixels to observe the fluctuation of OOD scores. From the table, we can see small random noise influence OOD scores, and the fluctuation of OOD scores is more remarkable with complex data like Cipher10. And OOD-aware models is more resilient than OOD-unaware models. After that, evasion attacks are performed to 4 OOD modules. We adjust the PGD attack to craft malicious perturbations. The attack goal is to acquire higher prediction confidence in perturbed OOD examples, that is evasive OOD data. This figure shows the changes of OOD scores before and after attacks. The first row is the original score, while the second row is the attack scores. And the first column and the third column are the OOD unaware models for the NetFi and the ResNet 18 respectively. It is found that OOD detection modules are vulnerable to evasion attacks. OOD-aware models are more robust than OOD-unaware models. As we can see in the figure, with less change. We also calculate the decrease of OOD scores and the attack success rates for evasion attacks. It is concluded that empty and cross-entropy techniques are more difficult to attack, and also highlight the superiority of OOD-aware models. For RQ3, we aim to identify the differences between OOD-unaware and OOD-aware models on model performance and robustness. We first evaluate the accuracy of different models on original training and tested data sets. Then, noisy in-distribution examples generated in RQ2 are used to evaluate robust accuracy. As shown in the table, the OOD-aware model seldom decrease the accuracy of training and tested data set, though irrelevant examples are added in the training process. On the contrary, it enhances the robust accuracy on noisy in-distribution examples. It also can be observed that with the increase of noisy ratio, robust accuracy decreases for all models. But again, audio-aware models are less affected. After that, adversarial attacks are performed to reveal the vulnerabilities of different DNN models to adversarial examples. The second and the fourth columns shows the average prediction confidence of initial states and the attacked examples respectively. And the third column records the attack success rate, and the last column depicts the audio-aware attack success rate. That is ASR after filtering out of distribution adversarial examples. From the table, though the average prediction confidence of different models on initial seeds are quite similar. The APC of all the aware models on adversarial examples is significantly lower than that of OOD unaware models, showing higher robustness to adversarial attacks. What's more, cross-entropy with OOD-aware models is able to filter all adversarial examples and achieve zero OOD-aware ASRs in all tasks. It provides us a new way to detect the adversarial examples. For IQ4, we investigate the uncertainty of OOD unaware and OOD aware models on in-distribution examples, evasive OOD examples, and in-distribution adversarial examples. One-shot execution metric and two Bayesian uncertainty metrics are used in our evaluation. And the direction of arrow denotes the direction of high uncertainty. The first row is the results for all the unaware models, and the second row is the results for all the aware models. From the figure, it is found that all DNN models have the lowest uncertainty on correctly classified in-distribution examples, regardless of DNN structures or training paradigms. Evasive OOD examples normally have higher uncertainty than in-distribution adversarial examples. And OOD-aware models tend to have higher uncertainty on all kinds of inputs. So at last, I'd like to conclude the gains and the suggestions provided in this paper. We hope the following gains is helpful to future research. First, model-based detection methods are better than data-based methods, among which cross-entropy with OOD awareness works best. And second, current OOD detection methods are vulnerable to evasion attacks. OOD-aware models are more resilient in the adversarial settings. Third, OOD awareness seldom decreases the model accuracy, but enhances the model robustness. And fourth, the uncertainty of DNN models on in-distribution, evasive out of distribution, and in-distribution adversarial examples are different. OOD awareness may increase the uncertainty of DNN models. We also highlight that the development of OOD-aware models is an important step toward trustworthy deep learning, and it is a promising practice to consider data distribution in the lifecycle of DNN models. So thanks for your listening. Is there any questions?
Thank you. Thank you very much for the nice talk. Very interesting work. So we have time for a few questions. Is there any question from the audience? Please feel free to just write your question in the chat if you have any. So while you're thinking, I may have one. So very interesting work actually, because this out of distribution data, detecting this out of distribution data is becoming more and more important to improve the robustness of and the reliability of this deep neural network. I was wondering if you have idea on how you could deal with data drift over time, right? Because the distribution.
What, sorry?
So when the model are deployed on the field, you have a difference between the distributions as the system is in production over time. So data drift. So difference between the
data shift.
Yeah, shift or data shift.
Maybe I make it clear. The question is about how do we define the out of distribution examples?
Can you hear me?
Right. Okay. Firstly, since the true distribution of the training data is not offered as an article in our paper, so we do not give very strict definition about what is in distribution or what is out of distribution. But we follow the common practice, that is, we just use the data from different domains to as an article for all the examples. Like for example, if we can say in the previous slide. Here. So here we train two classifiers. One is about MNIST and another is about Cypher 10. So for MNIST, the in-distribution example is just the training data and test data. And the out-of-distribution examples, we use the totally different data set for other tasks, like
I understand.
And also we
use Yes, I understand that. My question was more if we want to use this in practice, because in practice you will have your data set shifting over time, right? So if you have thought about this and you have any idea of how to handle it, if you are in that scenario.
So we can given a specific task, we can first we train all the aware models. That is, we in the training process we can we can try our best to collect enough all the examples and make the models learns the heuristics about what is indie and what is OD, and then we can use the detection method like the cross entropy matrix to detect in the real application. So
hello.
So in just like this, we can add an OD module and to calculate the OD scores for the given input, and if the scores is higher than the threshold, and then it will be regarded as an OD example and will be discarded. But also we should notice that because distribution shift is very common in the real world. So so you should update your models from time to time. You cannot always use the same model for a long time. Yeah. Hello. Hello?
Hello?
Yeah. Maybe the internet is not well.
Yes, sorry. I don't know. I think there's maybe a connection problem.
Okay.
Okay. So
Okay.
well, thank you very much. Do we have any other question from the audience? No? If not, let's thank our speaker again. So thank you. Thank you very much,
Okay.
Lingjun. Very interesting work.
Thank you. Yeah. Thanks for listening again.
Thank you. Very interesting work, actually. So our next speaker, the last in the session, would be about improving machine learning-based code smell detection via hyperparameter optimization. So please, can you share your screen?
Hello, can you hear me?
Yes, I can hear you.
Hi everyone. I'm honored to have chance to talk our research for you. At first, I introduce myself. I am a graduate student from Nanjing Tech University. At
Can you share
present,
the slide, please? The slide. We don't see the slide. Hello? Yes. Okay. Now we can see the slide.
okay.
Yeah, please go ahead.
At present, my research interests focus on machine learning-based code smell detection. This is a context of our paper, improving machine learning-based code smell detection via hyperparameter optimization. Next, I will show our paper from 5 parts. The first part is code smell. Code smell was first coined by Kent while helping Martin Fuller with his refactoring book. Fuller defined 22 types of code smells and introduced how to refactor these code smells. In our research, we mainly consider the 2 kinds of code smells, data class and feature envy. Data class is a class that stores data without providing complex functions, while other classes strongly depend on this class. And the feature envy is a function or method that often performs its own functional calculations based on the data from other class. Give 2 examples respectively. This is a Java code. The movie class contains many attributes, but its functions are all datasetters and getters, which are not complicated. Other classes are also intensely rely on movie. In this example, the data are used in the amount_for method are mostly from the renter class, but does not come from the costume class to which it originally belonged. The second part is motivation and research questions. Sorry.
Hello?
Sorry, I changed my PPT.
Okay.
Wait. Okay, let's start.
Okay, please go ahead.
The second part is motivation and research questions. Although code smell often does not affect the behavior of the software system, it will cause quality problems in terms of readability, understandability, and efficiency. There are two ways to detect a code smell. One is a heuristic-based method, and the other is a machine learning method. However, the former are often criticized by, number one, the rules need to be defined manually and rely on the experience of experts. Number two, the results of different tools are inconsistent in most cases. Number three, customized rules for a specific project are unavailable. The latter can overcome the shortcomings of the heuristic-based methods and become more prevalent. However, most studies ignore the hyperparameter optimization in the code smell detection field. Thus, we apply it to code smell detection and compare the detection performance of different machine learning methods in order to give researchers a good suggestion. In our experiment, we applied 4 optimizers. Grid search is an exhaustive searching algorithm. Grid examines every combination among all candidate hyperparameter spaces. Random search is similar to grid search. Instead of searching all candidate combinations, random limits the explored number by the specified number of iterations. Bayesian optimization intuitively optimizes hyperparameters based on historical results, which constructs a surrogate model to approximate the detection performance over all hyperparameter distribution. Differential evolution is one of the evolutionary optimization techniques. Most heuristical search algorithms are inspired by natural selection. After mutation and crossover, individuals in the population with high-quality genes may be preserved. In our experiment, we designed 3 research questions. RQ1, compared to the default values, whether using hyperparameter optimization can significantly improve code smell detection performance when considering different classifiers. RQ2, when the specified classifier random forest is given, is there a hyperparameter optimization method that has superior performance? RQ3, applying the parameter optimization to differential evolution optimizer, could our machine learning-based method achieve a better performance? In the third part, I will introduce our experimental design. Step 1, data collection. We mine datasets from QC, which have been widely studied in machine learning-based methods for code smell detection. Foutse manually sort the missing third-party libraries to reserve class dependencies and choose 74 compatible projects among them. We carefully verify Foutse's datasets and find issues related to data quality, such as sample sparsity and class imbalance, which may affect the experimental validation. Step 2, we measure their object-oriented features by using design features and metrics for Java tool. Step 3, for labeling code smells, we combine detectors and manual way to label. In this process, we first label with different detection tools. When we achieve a consistent result of all detectors, the modules should be labeled. Otherwise, they are labeled as unknown. Furthermore, for the unknown modules, we invited the three well-trained research to check out solely based on follows definitions. Finally, 8 of 74 projects are selected as experimental subjects, 644 modules with data class and 6,222 modules with feature envy. In our experiments, 6 well-established classifier families have been involved. To guarantee the generalization of our empirical results, we choose one representative for each family and implement them by person. This table covers the parameter settings in experiment. These parameters have obvious effects in classification problems, and they are also the main targets of defect prediction optimization. This is the process of hyperparameter optimization. Take random forest as an example. We have determined the table and the range of the parameter. Fitted the trained algorithm to the training data. Next, apply the learned model to test data and conduct 10-fold cross-validation to evaluate overall performance throughout the whole dataset. At last, we evaluate the model. AUC is a widely used evaluation module in machine learning and is insensitive to the class imbalanced problem. We conduct 10-fold cross-validation 5 times, and eventually cut with great search has to be conducted 24,300 times. Furthermore, to determine whether there is a significant difference between the two methods, we employ Cohen's distance effect size, which is widely studied by peer-reviewers, mining software repositories researchers. Cohen's distance equals mean difference divided standard deviation. In this paper, the difference between two methods is defined as large, medium, small, and negligible. The first part is experimental results. To answer RQ1, we first show the code smell detection performance of 4 optimizers and a default baseline on 6 classifiers for 2 code smells. Firstly, I show the result of data class. From the upper table, we can see that the default method is always the worst in a total of 6 classifiers. These results show that using hyperparameter optimization can improve the performance of machine learning-based methods, which is consistent with previous findings in software defect prediction. Compared with 4 optimizers, which is the best performer, followed by DE. We also calculate the average AUC of 6 classifiers, where random forest is 0.9424 and outperforms other cosmel models. From the bottom table, we find all 4 optimizers can acquire larger effect size in more than half of the classifiers. Secondly, this is the result of feature envy. From the upper table, slightly different from data class, we can see that default method loses 5 times in 6 classifiers, but performance based in rule. Grid is undoubtedly superior to other optimizers, followed by D and random. Look at the bottom. Most optimization methods, similar to data class, show a significant improvement in CT and KN, and have an improvement in random forest and SVN. To answer RQ2, we present with the performance of 4 optimizers on 8 projects by drawing the bar chart, where y-axis represents the detection performance. Notice that due to promising co-smell detection performance of random forest, the results of RQ2 are based on the classifier random forest. For the optimizers, we set the iteration number to 30 for a fair comparison. Firstly, this is a figure of data class. We find DE is always the best in a total of 8 projects followed by base, where the performance of grade looks similar to random, sometimes even worse than random. Similar in the result of feature anyway, DE slightly outperforms than other competitors. All the AUC values are over 0.93 on 7 out of the 8 projects, while on the worst WCT, the AUC also exceeds 0.9. The above findings imply that all optimizers have a positive influence on detecting co-smears, and we recommend DE because of its consistent performance of random forest. To answer RQ3, we mainly expect two impact factors. The number of pollutions and the number of iterations of differential evolution, which has been confined as the most effective method in RQ2. We repeatedly fix one variable as 30 and study the other variables variance at different values. The left up figure, we first consider the impact of factor pollution. As the factor pollution increases, the change of detection performance is quite limited, and the AUC values are mainly distributed between 0.951 and 0.952, particularly when pollution is set as 20 or 100. DE can reach its maximum predictive power for data class detection. The right upper figure, we consider the impact of factor iteration. Compared with pollution, the factor iteration has a significant difference on detection accuracy. We can find the AUC would gradually be improved when iteration starting from 10 to 50, but decline considerably after reaching 100. The best result appears in the case of iteration at 50. The result for feature anyway is similar to data class. From left bottom figure, when the factor pollution increases, the AUC values are slowly varied from 0.948 to 0.952. We also inspect the impact of factor iteration in the right bottom figure. By comparison with data class, we can find a consistent tendency across different values of AUC when iteration is less than 50. However, we continue to increase the iteration until at the value of 100. The AUC would drop dramatically to the worst performance of 0.939. All the observations indicate that DE would be affected slightly by pollution, but is sensitive to iteration. The reason for the above is mainly because the optimal individuals within a limited iteration process can be quickly evolved, so the prediction accuracy is difficult to be further improved by an additional evolution cycle. In the end, the last part is our conclusion and feature work. We have empirically studied the effect of hyperparameter optimization on machine learning-based co-smell detection. We find that for data class or feature anyway, the detection model with hyperparameter optimization performs much better than the default setting in most cases. Furthermore, we highly recommend other researchers to build a random forest model with DE-based optimizer for co-smell detection. In the future, we plan to conduct our analysis on commercial projects and conduct larger-scale experiments on more classifiers to verify the generalization of our findings. That is all my presentation. Thank you for listening. If you are interested in my research topic, please contact me. Thank you again.
Thank you very much. Thank you for the very interesting work. Nice talk. We have time for some questions.
Okay.
So if you have questions, please just type it in the chat or raise your hand. I have one question. So you did hyperparameter tunings. I was wondering, did you handle the class imbalance issue? Did you try with techniques like smooth to see how combining class imbalance issue and hyperparameter tuning, what kind of result you could have? Did you experiment? No?
Yes.
Because your data says you have a high.
My network is not good. Please repeat again.
So I was asking if you consider class imbalance issue, because smells represent just a tiny proportion, right, in your system. So you have highly imbalanced classes, right? And then there are techniques to solve that, like smooth, right? You can sample or subsample one class to the others to have the class more balanced so that the models behave better. I was wondering if you try combining that with hyperparameter tuning to see what you can get as a result. Did you hear my question?
Yeah, I can understand. And based on final empirical results, we find that using hyperparameter optimization can significantly improve the performance of co-smell detection.
So you did that without rebalancing the classes? No, you didn't rebalance the classes. No. Did you hear my question, my point?
Yeah, I can.
I mean, I think what you did is fine. So I'm just wondering if for some of the models that you had in the comparison, if for some of them you did rebalance the class, you may get maybe a bit smoother results.
We have 6 classification models in our research, 6.
Yes, but you're comparing them, right? So some are more sensitive to class imbalance than others. Like random forest, for example, is quite robust, right? But some other models are more sensitive. So if for those you did rebalance the classes, the difference with random forest may be smaller. You may find different. You could get some improvement on some of the models if you did resolve the imbalance issue. That's just
random forest is best model in our research.
It's quite robust. Yeah. I think that's consistent with previous studies.
Yeah.
Any other question from the audience? Any last comment? You can just turn on your microphone and speak if you want to ask a question. No? Okay. So thank you very much for the nice work. I think very interesting work. You study only 2 anti-pattern. Do you plan to expand to more?
Okay, thank you. Thank you.
Thank you. Thank you very much. And thank you all for attending the session. I think this is all for our session. We had only 3 papers in this session. So we will stop here and you can join the other session. Thank you, everyone. Thank you very much.